Hello and welcome to The Good, the Bad and the Ugly, Pitfalls and Best Practices in Automated Sound Static Analysis of Ethereum Smart Contracts. I'm Markus and this is joint work with my colleagues Clara Schneidewind and Matteo Maffei. So why are we interested in the automated sound static analysis of smart contracts? Smart contracts are distributed programs that handle financial assets on blockchains. Because of this, bugs in smart contracts can cause immediate financial losses. This is not only a theoretical concern, as such bugs have been exploited successfully in the past. One of the best known examples affected the DAO, a crowdfunding platform which had a bug in its function to withdraw invested money. In a normal use case, users could donate money and, under certain circumstances, retrieve it again. An attacker was able to steal money from honest users by deploying a malicious contract that first donated money and then retrieved this money again and again. Although these so-called reentrancy attacks are well known and understood since at least 2016, they still occur. While writing the presented paper, for example, there happened another attack where tokens worth $25 million were stolen. How can such incidents be prevented? One promising approach is the use of static program analyzers. Static analyzers can prove the absence or presence of certain problematic behaviors of programs before running them or deploying them, as with smart contracts, on the blockchain. A static analyzer has three different outcomes. It can label a program safe or unsafe, or can return unknown in the case a timeout is reached or the computation diverges. We are here particularly interested in automated and sound static analyzers. Automated here means that no further input but the program is needed to assess the safety of said program. Soundness in the context of static analyzers means that if a program is labeled safe, it is indeed free of problematic behaviors. That is, the analyzer produces no false negatives. Due to the financial nature of smart contracts, soundness is especially important. So far, all existing tools, even though claiming to be sound, fail to actually give such guarantees. This in particularly applies to the state-of-the-art tools Securify and SUSE. In the rest of this talk, we will see why it is so challenging to develop an automated sound static analyzer for Ethereum smart contracts, how previous tools failed, and what strategies can be used to achieve soundness nevertheless, using the example of our own static analyzer eThor. But first, let us overview the environment that makes analyzing smart contracts so difficult. In Ethereum, network participants try to maintain an append-only data structure at the blockchain from which they can compute the global system state. This global system state consists of user accounts that are owned and controlled by users and contract accounts that are controlled by their code. Then, the global state of the system is updated according to the transactions that are appended to the blockchain. These transactions transfer money, create new contract accounts, or invoke existing contracts. When a contract is invoked, its code is executed, and this code execution can trigger further interactions with other contracts. While contracts in Ethereum are usually written in the high-level language Solidity, before they are deployed, they are compiled down to EVM bytecode. This is an assembly-like stack-based language that features domain-specific contracts for environment access and also for interactions with other accounts. Let us now visit a simplified version of the DAO hack mentioned before. Our contract consists of a mapping between addresses and balances and two functions, invest and withdraw. By calling the invest function, the balance of a caller is increased with the value attached to the call. When calling the withdraw function, it is first checked if the caller has invested before. If this is the case, the investment is sent back to the caller and the balance mapping is set to 0. Although this contract seems secure, it is susceptible to a so-called reentrancy attack. Let us now consider a possible attack contract. To facilitate this attack, the attacking contract first invests a small amount of money. Then, in the actual attack, the withdraw function is called and the donated money is sent back. Due to a particularity in the Ethereum semantics, the attacker may now react on receiving the money and does so by calling the withdraw function again. Since the balances have not yet been updated, the attack contract sends back the invested amount again, upon which the attacker again withdraws and so on, until the attack contract is drained empty. A formal security property that prevents reentrancy attacks from happening is single entrancy. After being re-entered, a contract should not be able to call other contracts. What are the challenges when analyzing smart contracts in EVM bytecode? To achieve a sound and performant analysis, it is crucial that the analysis captures all possible behaviors of a program, but summarizes and simplifies them in a way that automated logical solvers, such as SMT solvers, can efficiently reason about it. What makes this particularly hard in the context of Ethereum is the smart contracts need to be considered reactive programs that interact with an unknown environment. So all possible effects of this environment on the contract execution need to be modeled. Next, EVM bytecode is not very suitable for static analysis. First of all, it has a non-standard memory layout, requiring to convert values when copying them between stack and memory. Secondly, it features very little static information. Jump destinations, for example, are not known upfront, but are computed on the stack, and hence the control flow graph is unknown. The way to cope with this complexity are on the one hand advanced domain-specific abstractions, and on the other hand preprocessing steps that recover as much static information as possible on individual contract instances. When doing that, one always needs to evaluate whether the chosen abstractions and preprocessing steps are still sound and really give a performant analysis tool. To this end, one needs to perform proofs, generate a tool, and conduct experiments, and based on the results potentially refine the abstractions and the preprocessing. This is a very cumbersome and error-prone process, since it technically requires to re-implement the analyzer in each iteration step. To understand where unsoundness might be introduced in the analysis, we can take a look at this schematic. Often the analysis starts with a form of preprocessing, such as control flow reconstruction. Then the actual analysis starts and tries to prove a security property, which is usually abstracted, meaning that it is only an approximation of the real security property. It is important that for any of these steps there is a provable relation to the corresponding entity. A preprocessing step may not alter the semantics of an input program, the analysis has to model all concrete execution behaviors, and the abstract property has to indeed capture all problematic cases. Of the tools presented here, all of them introduced unsoundness in at least one of these steps. Securify suffers from an unsound control flow reconstruction, has bugs in its dependency analysis, and provides some insufficient security patterns. Zeus changes the semantics of contracts by translating it to the input of the target solver, models reentrancies in an unsound manner, and treats security properties syntactically, thereby missing some of the semantic subtleties. Similarly, Neutschek's syntactical approach is insufficient to guarantee soundness. We will now look at some of these issues in greater detail. As mentioned before, the control flow in EVM bytecode is implemented by manipulating jump destinations on the stack. Since this dynamic element complicates the analysis, analyzers usually try to reconstruct the control flow in a pre-analysis step. The problem here is that the control flow may depend on the blockchain environment, which is unknown at analysis time. In such a case, a sound analyzer therefore has to either model all possible control flows or reject the contract as unknown or unsafe. An example for such an unsound control flow reconstruction is Securify, which fails to analyze the contract on the left. The jump destination at line 15 can be easily reconstructed to be always 4, while the jump destination at line 8 depends on the value that were on the stack when entering the block. In executing the program, we first don't jump, because the second value on the stack is 0. Then we populate the stack with information that is dependent on the blockchain environment and jump back. When hitting the jump at line 8 again, we don't know where to jump. In principle, all jump destinations would be possible, especially line 18, which contains bad behavior. Securify's control flow reconstruction, however, will return a trivial contract that is labeled safe. To illustrate the problems that might be caused by an unsound core analysis, let us consider this ostensibly fixed version of our simple DAO-like contract. Instead of using the balance mapping as a guard, we introduce a separate variable lock that prevents reentrancy attacks from happening. Such an approach would work in principle, but only if the lock cannot be influenced by other functions. In this scenario, the programmer mistakenly made a function public that can switch the value of the lock. The attacker now can use a modified attack in which switch lock is called before re-entering withdraw, thereby enabling again the original attack. An analyzer that is affected by this corner case is Zeus. Zeus works by translating solidity to an intermediate language, transforming a program depending on an analyzed property, and enriching it with assertions. The enriched program is then compiled to LLVM bitcode and analyzed with the existing solver chorn to check if all assertions hold. The program transformation for reentrancy replaces every call with the invocation of a copy of the surrounding function. Here, for example, withdraw is replaced by an invocation of a new function withdraw prime. In withdraw prime, the call is replaced with a false assertion, that is, an assertion that should be under no circumstances be reachable. The problems with this approach is that it fails to model problems caused by interleaved invocations such as the ones in the previous slide. The last source of unsoundness we will discuss is unsound security properties. One way of preventing DAO-like attacks is to forbid writing to the storage after performing a call. Securify provides an unsound compliance pattern for this property that characterizes it as a call instruction may not be followed by a storage instruction. The problem with this characterization is that the storage instruction is not necessarily needed to write to storage. Consider the contract on the left. It is in principle the same vulnerable contract as before, but the balanced mapping is now handled by a library contract. Such a contract can be understood as similar to libraries in regular programs and facilitate code reuse. The problem here is that, although the contract storage is modified, there is no storage instruction in the code of the analyzed contract. Instead, there is only a delegate call instruction which allows the library contract to modify the storage of the analyzed contract. Since the analyzed contract does not contain an explicit storage right, Securify mistakenly marks it as safe. So how did we address these problems in our own static analyzer eThor? First, we invented Host, an immediate language to specify the analysis on a high level, and that allows us to easily reason about the soundness of the analysis. Host allows us to give an analysis in terms of an abstract semantics in the form of horn clauses. Horn clauses are logic implications that can be used to describe abstracted execution steps. To prove the soundness with respect to real language semantics that we also formalized in a prior work, one can show that actually all real-world execution steps in a contract can be simulated by a sequence of abstract execution steps as they are described by the horn clauses. Based on this formalization in Host, we now wrote a compiler that automatically takes the Host specification of the abstract semantics and translates it to an analysis tool which then inherits its soundness guarantees, and that we can also use for empirically evaluating the performance of the resulting tool with benchmarks and test cases. How can we prove that a horn clause-based abstraction is sound? The general idea is that each concrete contract execution, which can be seen as a sequence of concrete configurations, can actually be mimicked by an abstract execution. So following the framework of abstract interpretation, one can define an abstraction function that maps a concrete configuration to its most precise abstraction, which is an abstract configuration that closely reflects the concrete original configuration. In our case, an abstract configuration is just a set of predicate applications. The abstract horn clause semantics describes how such an abstract configuration can evolve into another abstract configuration by logical deduction. In this process, the abstract configuration may lose precision. To express this, we ordered abstract configurations by level of abstraction. For proving soundness, it is not only important to show that for every sequence of concrete execution steps, one can also find a sequence of abstract steps where precision with respect to the concrete execution is at most lost. So we can say that each abstract execution ends up in an abstract configuration that is at least as abstract as the most precise abstraction of the corresponding concrete configuration. This connection shows that if we can exclude problematic behavior on the level of abstract executions, we can also do so for concrete executions. To give you an idea on how our abstract semantics in Host looks, we will now overview a few of Host's features. Host provides non-recursive algebraic data types that are automatically translated into more primitive types that the underlying solver can understand. Marked in red is the definition of the abstract integer domain. An abstract integer is either top, using the add t constructor, or a concrete integer that is wrapped into the add v constructor. We can also define non-recursive functions that are in principle hygienic macros. Here we have an overflowing addition on abstract integers. If both values are concrete, we add them together and apply the modulo. If at least one is top, we return top. The core of the semantics is specified as rules. The rule here is how we implemented binary opcodes in our EVM semantics. Rules are instantiated via a parameter interface. Here the instantiated rule has access to the operation it is modeling, the ID of the analyzed contract, the program counters of the modeled operation in the analyzed contract, and possibly some pre-computed arguments from the pre-analysis. We can use these values in the clauses specifying the actual semantics together with universally quantified variables such as x and y in this example. The exact details of this rule are out of scope, but in a nutshell it says the following. If the configuration at program counter PC has at least two values on the stack, the configuration at program counter PC plus 1 should have its stack size reduced by 1, and the top of the stack should be calculated by applying the operation described by OP on the two uppermost elements. Now we will have a look at how we translate our abstract semantics to optimized inputs for SMT solvers. The first input of our analysis is the bytecode of a contract that is extended with its control flow that was soundly reconstructed in the preceding step. This bytecode is parsed and a conservative pre-analysis propagates constant within basic blocks. The second input is a declarative specification of the abstract semantics in our own specification language Host, which can access data obtained in the first step via a parameter interface. The Host compiler then instantiates the abstract rules, translates high-level Host constructs such as types, operations, and bounded iterations to an intermediate horn clause format, and prunes predicates that are either trivially unreachable or irrelevant for current analysis. We then try to further reduce the complexity of a clause set by applying different transformations from literature. Since the efficacy of these transformations is dependent on the analyzed contract, we implemented different optimization strategies. In the last step, we encode the optimized clause set to SNTLib and invoke set3 on it. The big advantage of this architecture is that the EVM-specific part of the analysis is relatively small and mostly declarative. This makes it easy to experiment with different abstractions and allows for analyzing different properties and even different bytecode languages in the future when we're using most of the analysis engine. The different optimizations implemented in the analysis engine are semantics preserving and therefore independent of the input specification. Besides proving that an abstraction is correct, it is of course also important that the implementation of the analysis is correct and performant. To help with this, we not only employed classical unit tests, but also a custom property-based test suite that can generate thousands of synthetic test cases. These tests help to identify edge cases and regressions and can already give us an intuition about the performance impact of certain abstractions. Additionally, we encoded all 604 relevant test cases from the official Ethereum test suite. These test cases are quite simple programs, but are already more complex than our synthetic tests. We were able to solve 99% of these tests in less than 1 second, and in 85% of the cases we solved the test precisely, meaning that the abstraction we derived was the most concrete one. As a last evaluation, we conducted a large-scale experiment on the benchmark introduced with the Zeus tool. After taking care of some of the problems with this benchmark, like duplicates, we are left with 720 real-world contracts, which we analyzed for reentrancy bugs. For 712 of these contracts, we were able to manually establish the ground truth according to our formal definition of reentrancy and evaluate eThor and Zeus against it. As you can see in the graph, the majority of contracts in our benchmark were non-reentrant. You can see on the left side that eThor in the non-hedged area has more false positives marked in red than Zeus. This is due to the use of only sound abstractions. Looking at the right side, we see experimental affirmation for eThor soundness. There are no false negatives, while Zeus classifies many contracts deemed reentrant according to our formal definition non-reentrant. With regards to F-measure, therefore, eThor outperforms Zeus at 89 versus 20%. In conclusion, in order to implement an automated sound static analyzer, every involved entity, preprocessings, analyses, and security properties must be proven sound. Rigorous evaluation is important to ensure the correctness and performance of an analyzer. It is possible to aim for soundness while still achieving competitive performance. Lastly, it is beneficial to separate analysis specification from implementation. Our approach for this is Horst, a new specification language for the modular design of static analysis tools. Thank you for your attention.